Start in like 3 minutes. Ready? All right, hello. Let's get started. Can you see that? Kind of. I just don't want to turn it too much because then you'll be in the camera.
I can see it from here though.
Okay.
And it's not. It's
Okay.
working.
Good. All right. Well, hi everybody out there in internet land. We are going to continue talking about our chemical structures, but this time we're going to extend it a little bit and talk about some of the ways that we abbreviate these structures so that we can draw bigger structures and still know what we're talking about. So we talked about these rules and these ways of drawing some different isomers then class ended. So since class ended, I would give you a couple practice things to challenge yourself. So one would be draw all, whoa, what did I do? Sorry, hit something. Let's try it again. Draw all 5 isomers of C6H14. I'll give you a hint with this one. There's no double bonds or things like what we ran into with the C3 one, but there are actually 5 different ways of laying out those structures and only 5. So try those and see what you can find. Okay. Then I don't know how many. There are many, many, many isomers, so I'm just going to say draw some isomers of C5H10O. Because now we add another atom in there, there's lots of different ways that you can lay that out. So give those a try and let me know how they go, or if you're having trouble finding them, maybe next week or the week after we'll kind of look at what you got and if you found them or not. These are both pretty common, especially the first one, common practice problems for this topic too. So you could look them up, but please try it before you go look it up and see if you can actually draw them on your own before you find the answer. All right. So when we move to larger structures, we can't be drawing what we just did. We can't be using these Lewis structures all the time because they get too big. So let's draw one big molecule, and then we'll talk about some ways that we can abbreviate that. So this one's going to be have some carbon and some hydrogen. So I've got carbon with some hydrogens, another one. This carbon, we're going to have a double bond oxygen coming off of it. Then the next one, back to 2 hydrogens, and then 1 hydrogen, and then a double bond with 2 hydrogens. Okay, so this molecule now has 7 carbons, and we can calculate its or count up its molecular formula. So we've got 7 carbons, so that's C7. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and then we've got an oxygen. So that would be the molecular formula, and as we said in class, the molecular formula isn't really great information because you can imagine there's lots of different molecules with that same formula. We could have put the oxygen somewhere else, we could have put the double bond somewhere else, we could have done other stuff. You know, there's many isomers possible here. Also, it took a while to draw that. Let's say we were drawing some reaction schemes like you saw in lab today. It would take a while to draw this thing over and over again. So we need some shortcuts, some ways of abbreviating this. The first way that we're going to abbreviate it is called a condensed structure. And in a condensed structure, there's a couple different levels, I guess we could say, of it. Basically, what we're doing is moving the hydrogens onto the carbons they're connected to, because we know that they can't be in the middle. They can't be in between carbons because they only have one bond. So for example, this first carbon has 3 hydrogens connected to it. So if we, instead of writing that all out, if we said CH3, and then we said that that was connected to another carbon here, and we'll keep going and do the rest, but just for now, that's not really a problem because we know, now that we know some things about these molecules, we know that those 3 H's can't actually be in between the 2 carbons. They have to be over here because each carbon has to have 4 bonds. So let's go through and abbreviate the rest of the structure that same way. So the next carbon has 2 hydrogens. We condense those and put them directly on. Then we've got 2 more. Then we're not going to do anything about this oxygen because we don't exactly know how that is just yet. We will in a minute. Then we've got a CH2, and then a CH, and then a double bond to a CH2. So that's a way to draw a condensed structure. So condensing those hydrogens onto each carbon. Okay. Now, another reason that we use condensed structures is because it's easier to type on a computer because you can write CH3 and CH2 better than you can draw these things. But some of the things we've done here, like this oxygen coming off and this double bond, those are not so easy to type. So another way of doing a condensed structure is to actually squish everything together and not show those other things. And when there is something kind of coming off, like this oxygen, we use parentheses. So another way of writing a condensed structure is to go CH3, CH2, CH2, CO. Oops, we wouldn't have that line. And then CH2, CH, CH2. So this would be a lot easier to type like on a computer, but it's not quite as clear sometimes because, like for example, how do you know that there's a double bond there? The only way to know that would be to know that carbon has to have 4 bonds and actually kind of like think about splitting it up and being like, oh, well, if that carbon has 4 bonds, then there must have to be a double bond there. And so like chemically, yes, that's true. You could figure that out. Like you could figure out what the structure is, but it's not real obvious. So a lot of times, even if people want to do this kind of a structure that's really, really condensed, they'll still break stuff out just to make it a little bit clearer. So like a hybrid of these two might be CH3, CH2, C, and then we're still going to put the double bond O, and then CH2 and CH, and the double bond to the CH2. So that's kind of like a nice compromise where you got everything smushed together. It's relatively easy to type, except for maybe that double bond to O, but it's definitely way more clear than the middle way of doing it. So that said, these are all correct versions of what we could call a condensed structure. There's no like absolute, this is a condensed structure and this is not. Like all of these are okay. So the idea is just to give yourself some help in drawing the structure more quickly. All right, a couple other abbreviations you might see for condensed structures. We talked about parentheses with that O, but a couple other ones you might see is sometimes they are at the beginning of a structure. So if we had something like this, CH3 taken twice and then CH3, we have to be a little careful there. That doesn't mean CH3, CH3, CH, CH3. And the reason that doesn't work is because this carbon now has 5 connections, 5 bonds, and this carbon only has 3 bonds. So that doesn't work. So that's the wrong structure. The correct structure would be to actually have both of those CH3s connecting to the CH. Like that. So that's when you see those parentheses at the beginning, and it's something like CH3 that can't be connected to itself like that, this is generally what's going to happen there instead. Does that make sense to you so far? When the parentheses are inside the chain, you can see a couple different examples of what people do for that. So one example is for very, very long chains. Where you've got the same thing repeating over and over again, like when we talk about biodiesel and fats and things like that, we'll use this abbreviation. You can use a CH2 in parentheses with a really big number, and that just means a whole bunch of them in a row, just connected to each other. Because we know CH2 can just go CH2, 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 and all those carbons will have 4 bonds, and that's fine. So that one just stretches out. If you see something that can't stretch out, it probably means it's coming off of the chain. So if we have instead like CH3, CH2, and then a CH3 in parentheses, sorry, that should be CH then, not CH2. CH3, CH, CH3, CH2, CH3, something like that. We know that CH3 can't be in the middle of the chain because there wouldn't be enough bonds, or there'd be too many bonds for that carbon and not enough for this other one. So what this means is that the CH3 is actually coming off of the CH, like that. And because that's kind of just, I don't know, it just feels sort of clunky and confusing to me. I don't like to use that, but like I'm telling you because you might see them in other structures, but I would always draw this like this bottom way just because it's clear that way and you know how those things are connected together that way. All right, so that's condensed structures. Any questions from the internet world there? Any questions from here? Okay. All right, so then we'll move on to the third way of drawing structures, which is both the easiest in terms of like drawing, but also the hardest in terms of like figuring out how to do it. And that's what we call line structures. And this is what we'll spend a little time trying to figure out and get. So I'm going to introduce it and kind of show you how to do this today, and then you can kind of work on it, and there's a lot of practice materials on Teams, and then in 2 weeks after the evaluations, we'll come back to this again and do even more practice and maybe some in-class work to work on this stuff as well. Okay, so with line structures, that's where we get these things that you might have seen like this. These are extremely quick and easy to draw, and this is how most chemists communicate their structures because they're so quick and easy to draw. But if you don't know what this sort of a thing means, then it's not real helpful. So we're gonna go through this, how to draw these things, what they mean, and we'll use some of our same examples that we had up here. So let's go back to that first C3, or those C3H6 examples we did in class today. I'm just going to redraw them down here so we have them. Now we should be able to take what we originally drew as Lewis structures and then also draw them as condensed structures and as line structures. So this is the Lewis structure for this one. Then we'll draw a condensed structure, and then we'll draw this new line structure. So condensed structure means we just put the hydrogens down on the carbons, and if we want, we can collapse the bonds also, or we can leave them alone. I would probably do kind of a hybrid thing here and draw this as CH3, CH, and then a double bond to CH2. But as we just talked about, there's various ways of doing this that would all be considered correct. So you could have the line still there, you could have no lines, that's all okay. All right, so now for a line structure, we're going to draw something very different. The line structure for this molecule looks like this. All right, we'll come back to this and kind of explain it, but I just want to put a couple examples up there first. Okay, let's look at the other one, the triangle one. If you remember, this was another Lewis structure of C3H6. We could also draw that as a condensed structure. And in this case, I would definitely keep the lines because otherwise it's really going to be hard to tell if you just draw like CH2, 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 how do you know that those are connected together? So I would keep the lines there and just draw like this so you can really see. And the more three-dimensional structure gets, the less you can really condense it and have it still make sense. So then the line structure for this one is just literally a triangle. So hopefully you're starting to see some patterns here in terms of where these line structures come from. First thing to note is the carbons. So in this first structure, we have 3 carbons. I'll number them 1, 2, 3. Carbons 1 and 2 have a single bond. Carbons 2 and 3 have a double bond. So you can see in the line structure, if we imagine 3 carbons at those positions, we have a similar type of structure. A single bond between 1 and 2, double bond between 2 and 3. If we do the same thing down here, let's just go 1, 2, 3, even though these are all kind of the same. We, again, are showing 3 carbons. So what might you guess as a rule for how carbons are expressed in a line structure? I don't know if anybody's on the comments here, but you want to give it a try? Oh, like where do the carbons go in a line structure? Like what stands in for carbons? Yeah, they're anywhere that lines either connect or end. So you've got like an end of a line over here, you've got a connection here, and then you've got an end. And in the triangle, it's like all the connection points. So our first rule of line structures is that carbon atoms are are expressed by ends of lines and intersections. That also kind of explains this zigzag. With Lewis and condensed structures, we drew everything in a straight line going across. But with a line structure, we have to kind of zigzag because otherwise we don't know how many carbons are expressed in a given line. And this way we can clearly see, okay, carbon, 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 carbon going across. That also happens to mirror the actual structure, the real physical structure of carbon atoms, which don't connect with these 90-degree bond angles, but actually do this zigzagging instead. So it works out that way as well. Okay, so that's our first rule. Carbon atoms are expressed by ends of lines and intersections of lines. So the other thing that's missing in the line structures is hydrogens. Why are the hydrogens missing? Or like, where are they? And the answer is, it comes back to this rule. If we, go way back. If we can assume that carbon is always making 4 bonds, then we can look at something like this, and we can say, all right, well, if this carbon number 3 has 2 bonds showing, then there must be 2 hydrogens there to make 4. So we can always assume however many hydrogens we need to get that count up to 4. And that's why we can do that for line structures. That's why we don't have to draw the hydrogens. So the second rule then is we assume there are enough hydrogens so that carbon has 4 bonds total, each carbon. So even though the hydrogens aren't shown, if we look at like the triangle here, if we just take one of those carbons, we look at like number 1 here, we can see 2 lines coming off of that. So that's 2 bonds that are connecting to carbon 1. And so then we can assume there must be 2 more hydrogens to make it up to 4 total connections. So one thing that can be helpful for practice with line structures is take a molecule like this one we drew up here and find its molecular formula. So if you're watching not live, this would be a good time to pause the video and actually give this a try, and then come back and we'll do it together. So here we're going to look for carbons at each intersection, and if you've got this in your notes or on wherever, you can actually draw it directly on here. So let's do that. So anytime those lines intersect, we can find a carbon atom. And then also this very end of a line is a carbon atom. We don't see carbon at this end here because that's connected to an oxygen. So that's going to be, make this a little bit clearer. So we're not saying that there's a carbon at the end of this line because the oxygen is already shown there. But we can get carbon as our first element, and if I add those all up, we've got 9 of them. So that's C9. Okay, then we can put in the hydrogens. So we know that there have to be enough hydrogens at each carbon so that each carbon has 4 total bonds. So if we start over on the right here, this carbon has 1 line coming off of it. So that means it must have 3 hydrogens to get up to 4 total. Moving over, we've got 4, so there's no extra hydrogens here. This one's got 2 connections, so that means we need 2 more for hydrogen. Then moving over here, we've got 3 connections to that carbon, so we can put in a hydrogen. And then all the rest of them around this ring have 2, so that's going to be 2 hydrogens for each of those to bring the total count of bonds to each of those carbons up to 4. So we can count all those up then. We've got 2, 4, 6, 8, 10, 11, 13, and 3 is 16. 16 total hydrogens. And then the last thing is the oxygen as part of the formula as well. So the formula of this molecule would be C9H16O. And in one of the documents linked in the module, there's a whole bunch of these that you can practice and work on and do this exact same thing. So that's one way to kind of make sure that you can decode line structures, that you can understand what they represent. The other way is, can you draw them? So let's try that. In order to draw them, we need a third rule, which is other types of atoms, so not carbon and hydrogen, and the hydrogens connected don't change. So you can't abbreviate oxygen or nitrogen or something like that. You can't leave the hydrogens off because they're not as predictable as carbon. We can't just assume how many hydrogens are supposed to be there. That only really works for carbon. So for an example here, let's look at this condensed structure, CH2, CH, and then I'm going to put a Cl on here, as well as an OH on the end. So let's say we want to turn this molecule into a line structure. All right, so what I would do first is try to find some sort of like long chain or some like how many carbons are connected together, some kind of basis. And so like here, clearly going across from left to right, I can count 1, 2, 3, 4 carbons in a line. So that's going to be my first starting place, is to just number those carbons off. All of these structures that we're looking at are based on carbon. That's what we call organic molecules. And so we can sort of always start with carbons as our basis. So we want 4 carbons in a line. The way we draw 4 carbons in a line structure is a zigzag where we're counting as many as we need. So we go 1, 2, 3, 4. And it doesn't matter if you start it going, can't tell if I'm mirrored here or not. 1, yeah, I am mirrored. So it's like 1, 2, 3, or not mirrored. So it's, yeah. It doesn't matter if we start going up or if you start going down, whatever. But I've got 4 carbons, and I'm just going to put numbers on there just to keep track as well. So there's 1, 2, 3, 4. And now once I've got that basic shell, I can add other stuff that's connected. So on carbon number 2, there's a chlorine atom. And so I'm going to add that here. And the reason that I add it upwards instead of down is because we always want to maximize those angles, so that they're not like all squished together. It's not wrong exactly. Whoops. What did I do? I don't want to do that. Go away. No, I don't want notes. How do I make it go away? Okay, I don't have to. All right, well, I can put it over there at least. Okay, sorry, so I was putting this here. So you could put the chlorine down from number 2. That would not be considered wrong to do that. But that's not usually how we see them. It's a better practice to try to maximize those angles. So you won't usually see it like that. You'll usually see it like this. And then over on carbon number 4, there's an OH. And there's 2 different ways we could put it. We could do it like this, straight up. Or we could go off and kind of continue the zigzag like that. Either one is fine. So notice nothing changes with the Cl and nothing changes with the OH. We don't drop the hydrogen off. We don't do anything with those. We just put them in as is. And so then it's always a good idea to go back and check, is everything connected to the number carbon that it is supposed to be? So in the original structure, Cl is connected to CH, number 2, and that's the case here as well. And then the OH is on number 4, and that's the case here also. All right, and that's basically how line structures work. The basic idea is not super complicated, but it does take some practice to get used to it and doing this. So in the document on Teams, there's a whole bunch of practice problems where you can try this out in lots and lots of different structures and see if you can draw these correctly. There is not an answer key for that page, so that is because I want you to actually do it and then either talk to each other or come talk to me about your structures and we'll see how they look together. That's a good thing to do in lab when you're waiting for something to finish. I think the next lab in a couple weeks is a reaction where there's some downtime where you have to wait for the thing to finish reacting. So that's a good time to talk about that, work through that stuff together. And as always, let me know if you have any questions. Any questions on this stuff so far? Okay. All right, thanks everybody.